So when we okay, test. Okay. Is it on? Everyone's.
Yes, sir.
Yes, sir.
Angeli show up. Okay, good. Okay, so let's continue. Hopefully, no technical problem again. So yeah, we speak about line defects. Yeah, so whenever we pull, for example, a rod, yeah, or a bar of material like this, yeah, is what we call as using a tensile stress. Okay, so what is the process actually until that material becomes broken? So what occurs is actually there is this formation of defects, yeah, a formation of defects inside that material. Yeah, that then the defects, when we pull further and further, yeah, the stress is larger and larger. Or the stress is maybe the same. The strain, I mean, the strain is larger and larger. Then, but there will be formation of defects. Yeah, more and more of line defects will occur, which eventually will cause fracture in that material. So after a tensile elongation like this, slip steps will occur. So the slip steps usually will form along certain crystalline plane. Okay. In linear defects, these are, or dislocation, yeah, the other name. These are basically one-dimensional defects around which atoms are misaligned. There could be two types. There are two types of linear defects. The first one is what we call as edge dislocation. This is an extra half plane of atoms inserted in the crystalline structure. The factor B, what we call as the Berger factor, and this is a measure of the distortion of the lattice, measure of lattice distortion. In edge dislocation, the factor B is perpendicular to the dislocation line. In screw dislocation, the Berger factor is parallel with the dislocation line. This is a spiral planar ram resulting from shear deformation. So what is shear deformation? So if you have a material like this, yeah, for example, if you fix one of the side of the material to, let's say, a surface, yeah, a solid surface which is completely immovable, not moving, and you push, yeah, you push or you pull this material in only one of its side, yeah, not uniformly across the cross-section area, but let's say only on one of its edge like this. So what occurs is that it will deform, right? It will deform, but deformation will look like this. So the upper part will deform more compared to the lower part, because the lowest part, the bottom surface is fixed onto this immovable thing, whatever it is. Yeah, so when you push or you pull with a force like this, only the upper part will move. The lower part will tend to stick. Yeah, the higher the position, the more deformation it will occur. So this is screw dislocation. Yeah, this is screw dislocation that occurs. There will be spiral planar ram resulting from the shear deformation. The Berger factor in this case will be parallel to the dislocation line. So this is in edge dislocation. Yeah. This is the Berger factor, which is in perpendicular to the dislocation line. Yeah, the dislocation line itself is vertical in this case. Then the Berger factor will be perpendicular to it, yeah, horizontal, yeah, like this. Okay. This edge dislocation can then also move, yeah, or has motion. Yeah, for example, in the previous example, when we pull the bar, a rod, yeah, using tensile strength, maybe the edge dislocation will first occur in the middle. Then when the pulling still occurs, yeah, continuously, this edge dislocation will move towards the edge. This edge dislocation move towards the edge until they becomes deformed, until the material deform. So this the motion of this dislocation requires the successive bumping of a half plane of the atoms from left to right. So in this case, this one will bump the atom, this plane will bump to the neighboring right plane. Yeah, so this actually it's still the same, but it looks like the dislocation move, yeah, towards the right, for example. So this, if we push to the right, yeah, for example, and this plane of atom will form binding with this line of crystal, and so the dislocation will occur here, yeah. And then etc. Yeah, until we push until it appears, this plane appears on the right side edge of this material. Okay, the bonds across the slipping planes are broken and remade in succession. Yeah. So the bond here will be broken and then make bond with this one. So this will have no bonding, so it will appear empty. So this emptiness, yeah, of edge, yeah, will move to the right, and then this broken again, then made binding with this upper half of this plane, etc., etc., until it looks like the edge dislocation move to the right. Okay, something like this. Atomic view of edge dislocation motion from left to right as crystal shear. In screw dislocation, this is occurs to shear deformation. So this is the dislocation line. Yeah, the Berger factor is located in parallel with that dislocation line. So dislocation line is in this direction, yeah, in this direction, and the factor also in that direction, the same plane, the same direction. So they are in parallel with each other. Yeah, this is what occurs. So it doesn't occur along the whole material axis, yeah, on the horizontal axis, but rather on one part of it, and then it is being slid to one another, being sheared. So this is how it looks like from one side. So if we look from this face, this how it looks like. Yeah, this A, this is A corresponding to this A, etc. Yeah. Then this is what occurs. Only one part of it move to the right. This still to the left. So when we push further, this will also can have a dislocate motion. So both edge and screw dislocations can occur at the same time, which will make a mixed dislocation. So here we have a mixed dislocation. We have this component is from the screw dislocation, yeah, this Berger factor here, while this component is edge dislocation because it is perpendicular to this line, yeah, to this line dislocation. Okay, so it will occur in 3 dimensions from top, yeah, from top. So will look like this, something like this. Yeah. This is edge dislocation, this part, and this one is the screw dislocation. So what will happen then, we will have mixed dislocation. How in actual material do we see such dislocation? So usually dislocation can be seen using electron micrograph. So the material first has to be polished. The metal material has to be cut and then polished, grain, and polish using certain similar like the sandpaper, but with machining, so that it can be very clean, very smooth. Then when you put under electron microscope or under actually optical micrograph with high magnification can also do, you will see the boundaries between the crystal. So, but the dislocation will be made more visible compared to the normal grain boundaries. So this is how it looks like, the dislocation in actual electron micrograph. So from here, then the engineer, you can analyze whether it is an edge dislocation or a screw dislocation or a mixed dislocation. So in the structure, close packed planes and directions are preferred for a crystalline structure to be to be stable. For example, here this is a view of a material in to a close packed plane. The close packed plane from top. This is the close packed direction. So if you see here, this is hexagonal close packed. They are completely packed. Hexagonal close packed is almost similar to FCC. So it has the closest pack, though the AFP, atomic packing factor, is the highest. Okay, remember AFP from the previous chapter. So in FCC, it has many close packed planes in direction, while in HCP, only one plane in 3 direction. BCC has none close packed structure. So when we pull using tensile structure, this is what occurs. Since FCC, in HCP, like magnesium, has only one plane, like this, only one plane of close pack in 3 directions. This is what will occur when you pull. The fracture will occur like this, almost like a line, but like a more of a straight line. However, in FCC, since it has many close packed planes and many close packed direction, you see here that the dislocation will also occur also along the line of this material. So in magnesium, for example, the width still stay the same. When it breaks only occurs at the ends of the 2 parts. But in FCC structure, like in aluminum, and when it breaks, the structure will also the dislocation or the edge the line dislocation will also occur along the length of that material, of that bar. Okay, now we discuss about 2-dimensional defects. So line defects is 1-dimensional. Point defect, like interstitial, substitutional, they are 0 dimension. There could also occur planar defects, which basically are 2-dimensional in nature. So one case is a twin boundary plane. Essentially, it is a reflection of atomic position across the twin plane. This is a twin plane boundary. But however, see, the 2 crystal have different orientation. One is like this, horizontal, and the other one make an angle towards the horizontal plane. So, but they have this joint or twin reflection of atomic position in this boundary. Another case of planar defects is stacking faults. We have learned in previous chapter, but for face-centered cubic metals, the actual sequence of stacking should be A, B, C, A, B, C. Remember the hexagonal structure when we put the second stacking, the third stacking. In FCC, the second stacking will have the second stacking layer of the atoms will have different position than the first. The third layer atom will have different position than the second and the first. When we come to the fourth, then it will repeat again the first position of the atom. So A, B, C, stacking sequence. However, fault or defect may occur, yeah, in two-dimensionally. For example, when instead of ABC, the stacking occurs ABC, AB, ABC, for example, here. In this, how many? 6 stacking, it should have been C. However, somehow what occurs is another A, another position of atom similar to A. So this will create planar defects in that solid. So all of these defects can be examined through microscopic examination. Yeah, we use crystalline grains and grain boundaries, which vary considerably in size, and that could be large. That's why they can still be observed using optical microscope. Yeah. Example like large single crystal of quartz or diamond or silicon, aluminum, light post or garbage. You can see the individual grains. Crystallites or grain can be quite small in millimeter or less. That's why it is necessary to observe with a microscope, but not that small that it needs electron microscope, for example. On ordinary optical, not ordinary, but usually metallographic optical microscope can be used. This one, that what I meant. So optical microscopy can magnify 1,000 times, 2,000 times. Yeah? Sometimes when it's better, could be a bit larger. So first is you have to grain the plane, one of the plane, and polish. Yeah, using scratches. Yeah, remove surface feature like scratches, so it's really smooth. Yeah, so that then the reflection will occur just because of the crystalline plane of that grain. So then you also do etching using in certain chemicals to change the reflectance, which will depend on the crystal orientation. So here, what occurs is when between the different different grains, each grain will have different crystallic orientation. So this will reflect the light, because we are speaking about light microscope. The light comes also from this objective lens. Yeah, due to this different crystallic orientation, will reflect a different direction. So when we observe it under microscope, some which reflect less will be observed like a black surface, while the grain that, for example, very smooth like this, which means it has a horizontal crystallic orientation, will reflect the light the most, so that it will appear as very bright. So this is an example of brass, the copper zinc alloy. Remember, I think we discussed about copper zinc alloy in the previous point defects solution. Brass, ya, perunggu, ya, brass in the bahasa Indonesia. Okay. So besides the crystallic orientation in one single grain like this, okay, using optical microscopy, we can also observe the boundaries, the grain boundaries. Yeah, which is basically also imperfection. The grain boundaries are either line imperfection or could also be plane imperfection. So they are imperfection, and these grain boundaries are more susceptible towards etching. We etch using certain chemical etchants, yeah, chemical solution, and they will be revealed as dark line because the light in the grain boundary will be reflected away, and they are not reflected back towards the lens lens objective, yeah. And it represents change in crystal orientation across the boundary. So it is illustrated like this. When we have polished the surface of the metallic material, we have etched them using chemical solution. Yeah, this what will occur in the grain boundary. In the surface, it will occur like this. Yeah, so it has like this kind of surface. So when light reflects, it will not be, when light hit that surface, it will not be reflected back towards the microscope. Instead, it will be reflected away, yeah, to to the side, like this, yeah, towards the side. While on the other part of the crystal, it will be reflected back, more or less will be reflected back towards the microscope. So as a result, this boundary will appear like, yeah, in a darker color compared to the poly surface. This is how it will look like. So the blacker, there is no, the darker line here represents the grain boundary of this material, iron chromium alloy. So based on this, we can estimate the number of grain, yeah, per square inch at 100 time magnification, and using this formula, n equals to power n minus 1, where n is the ASTM grain size number. ASTM is American Society for the Technical Mechanics, if I'm not mistaken. So this is a standardization body in United States for metal and material. We can also use polarized light, yeah, to increase the contrast in optical microscopy. Polarized light means that light, you know, as you have learned maybe from physics, yeah, that has the electric field component and the magnetic field component. When you put them into a polarizer, only one field of the electromagnetic wave will be passed through. Here is polarized light. And metallographic scopes often use this polarized light to increase contrast. And also use this polarized light also used for transparent samples such as polymer. Because if in metals, the surface will reflect the light, right? That's why we can see the, like this, we can see either dark or bright, yeah, which will depend on the crystallographic plane orientation, or like this, we can see the boundary line, yeah. But in polymer, since mostly they are made from carbon, oxygen, hydrogen, nitrogen material, they are light material, light atoms. They are transparent, yeah, in light, especially when you make small thin sample. And then we can use polarized light to observe the structure. Optical resolution like 10 to the power of -7, yeah, or 0.1 micrometer or 100 nanometer, yeah, for light microscopy. If we want to observe the material at high resolution, then we will need higher frequency or smaller wavelength of probing of the probe light, yeah, probing wave. We could use X-ray, yeah, which is difficult to focus, but actually there is in recent year, at least 10 years from now, 10 years ago, yeah, not 10 years, 10 years ago when I was in Malaysia, there I already met one of the vendor who make this X-ray microscope, XRM, X-ray microscope. Of course, yeah, it is difficult to focus, but they made this kind of X-ray lens, using electromagnetic lens. Alternatively, of course, the more widely available microscope now is to use electrons. Yeah, the wavelength could be as small as 3 picometer. This is 0.003 nanometer. Yeah, so actually even less than the diameter of an atom. Yeah, the magnification would be made even up to 1 million times. So that is why you can resolve atomic resolution at very high magnification and high resolution electron microscope. You can resolve atomic resolution. Once I went to Japan to one of the company that built this electron microscope, I observed that time the silicon crystal, silicon crystal that is used in electronic industry. Really, the silicon atom configuration at atomic level resolution. That was quite remarkable experience because we could see with our eyes. Well, of course, with the help of the microscope, the the atomic resolution of the structure of that material at atomic resolution. In this case, this electron beam is focused using magnetic lenses. We could also use to observe the material structure of the crystalline structure using scanning tandem microscope. However, the material need to be prepared specifically. The atoms can be arranged like this and even imaged. The STM here can also be used not only to observe, but also to interact with the atom. For example, here atoms can be assembled in, of course, in specific, very smooth, atomic smooth surface. You can assemble this atom to form a certain form like this. This is carbon monoxide molecules arranged on platinum at 111 surface. This is iron atom arranged on 111 surface of copper to build genshi in Japanese, which represent atom, the word for atom. So in summary, the point, line, and area defects exist in solids. The number and types of these defects can be varied and controlled. Usually the temperature controls the vacancy concentration. Defects will affect the material property, like the grain boundaries will control the crystal slip, and depending on the plane, HCP, FCC, like what we have given, how when you pull, the defect will occur depends on this plane, the crystalline structure also. Sometimes defects are desirable. Sometimes you don't want a completely perfect crystalline structure. You want something else. But sometimes also undesirable. Maybe good or bad depending on whether plastic deformation is desirable or not. Okay, so I think that will be all for the first session.